Welcome to this session again. We are discussing the question, the answer regarding thermochemistry. Last time we ended on question 20. Today we are going to start on question 21. Question 21 is saying 0.24 kilogram of hot metal at 150 degrees Celsius was dropped into a beaker containing 0.15 kilogram of water at 21 degrees Celsius. The final temperature of the mixture was 27 degrees Celsius. They are asking what is the specific heat capacity of the metal. The specific heat capacity of the water was given as 4,184 joule per kilogram degrees Celsius. We need to determine the specific heat capacity. Let's see the answer. We have a metal which is hot with 150 degrees Celsius, and the water which is not hot, which is having 21 degrees Celsius. There will be a flow from the hot metal, a flow of heat from a hot metal to water. That means the heat gained by the water will be equal to the heat lost by the metal. The metal will lose the heat and water will gain the heat. The mass of water times the specific heat capacity of the water times the change in temperature of the water will be equal to minus the mass of the metal times the specific heat capacity for the metal times the change in temperature of the metal. We are putting minus because the metal is losing the heat. We have all the data. We can replace the values. We have the mass of the water, which is 0.15 kilogram. We have the specific heat capacity of the water, which is 4,184 joule per kilogram degrees Celsius. We have also the change in the temperature of the water, which is 27 degrees Celsius minus 21 degrees Celsius. The final temperature of the water and the metal is 27 degrees Celsius, and initial temperature of the water is 21 degrees Celsius. This will be equal to the mass of the metal. It was given as 0.24 kilogram times the specific heat capacity of the metal, C metal. It was not given, so we need to calculate this C metal. Then times the change in temperature for the metal. The final temperature of the metal was the same final temperature with the water, which is equal to 27 degrees Celsius. Then the initial temperature of the metal was 150 degrees Celsius. Here then we need to calculate this unknown which is the specific heat capacity for the metal. If we can calculate the C metal, we are doing some of the multiplication so that we can get the C metal. The C metal, which is the specific heat capacity for the metal, will be equal to 127.56 joule per kilogram degrees Celsius. That means that the specific heat capacity of the metal is 127.56 joule per kilogram degrees Celsius. Let's see question 22. Question 22 is saying the amount of heat needed to raise the temperature of 541 milligram of sample of C9H10O2 from 47.1 to 62.8 degrees Celsius is 14.3 joule. So this is the heat that is given. What is the molar heat capacity for C9H10O2? Let's see the answer. Here we have the heat and we have the formula for the heat, which is equal to the heat is equal to the molar heat capacity, the heat capacity times the change in temperature. That's the one formula. The second formula is that the heat is equal to the mass times the specific heat capacity times the change in temperature. The third formula is that the heat is equal to the number of mole times the molar heat capacity times the change in temperature. So in the question they're asking this molar heat capacity. So we can use this formula to calculate the molar heat capacity. We have the heat that was given as 14.3 joule. The heat was given as 14.3 joule. So the number of mole, we don't have the number of mole, but we can calculate from the mass. We know that the number of mole is equal to the mass dividing with the molar mass. But we need to change this mass into gram. So let's calculate the number of mole. We have the molar heat capacity, which is C is equal to Q dividing with the number of mole times the change in temperature. So from this formula, we can find that the molar heat capacity, which is C, is equal to Q dividing with number of mole times the change in temperature. So the change in temperature, here the change in temperature was given. We have the final temperature, which is 62.8, and the initial temperature, which is 47.1, and the final temperature 62.8. Let's calculate the number of mole. The number of mole will be equal to the mass, which is equal to 0.541 gram, dividing the molar mass. The molar mass for the compound for C9H10O2 is equal to 150 gram per mole. So we need to take the 12. Molar mass of carbon is 12. We need to multiply with 9. Molar mass of hydrogen is 1. We multiply with 10. And the molar mass of oxygen is 16. We multiply with 2. Then we add and we obtain 150 gram per mole. That is how we have obtained the molar mass of the compound. And the number of mole will be equal to 0.0036 mole. Having the number of moles and having the change in temperature, then we can calculate the molar heat capacity, which is equal to Q dividing with the number of mole times the change in temperature. The Q was given as 14.3 joule, the number of mole 0.0036 mole, the change in temperature, the final temperature minus initial temperature. Then we get 253 joule per mole degrees Celsius as a molar heat capacity. Let's move to question 23. Question 23 is saying how much energy is required to heat up 5 mole of water from 20 to 50 degrees Celsius. The molar heat capacity of water was given as 75.4 joule per mole degrees Celsius. We need to calculate how much energy is required to heat 5 mole. So that is the Q. How much energy is Q to heat 5 mole? The number of mole was given from 20 to 50 degrees Celsius. That means the 50 will be the final temperature and the 20 will be the initial temperature. Here we can calculate the change in temperature. The molar heat capacity of water was given as 75.4 joule per mole degrees Celsius. Here we need to use the formula and replace the values. We know that Q is equal to the number of mole times the molar heat capacity times the change in temperature. So here we have the molar heat capacity of the water, we have the number of mole, and we have the change in temperature. So we need to only replace the value. We have 5 moles, we have the C, the molar heat capacity of the water, which was given as 75.4 joule per mole degrees Celsius, times the change in temperature, 50 degrees Celsius minus 20 degrees Celsius, and we get 11,310 joule as the energy required to heat up 5 mole of water from 20 to 50 degrees Celsius. Let's see question 24. Question 24 is saying it takes 80,860 joule of heat energy to raise the temperature of 80 moles of substance. Here the heat was given and the number of mole was given from initial temperature 25 to 70 degrees. The final temperature was given as 70 degrees. Calculate the molar heat capacity of this substance. Here also we will use the formula where we have the Q, which is the heat, is equal to number of mole times the molar heat capacity times the change in temperature. Then this molar heat capacity will be equal to Q dividing with N times the change in temperature. So the molar heat capacity will be equal to Q dividing with molar heat capacity will be equal to Q, the heat, dividing with N times the change in temperature. We can replace the values. The heat was given. So the moles, we have 80 moles, and the change in temperature is to be equal to 70 degrees Celsius minus 25 degrees Celsius. So here, then we get the final answer where we have the molar heat capacity is equal to the value that you see. Let's go to question 25. Question 25 is saying you have 2 moles of a metal at 150 degrees Celsius. It was added at 10 mole of water at 20 degrees Celsius. We are adding 2 moles of a metal with high temperature 150 to 10 to the water with 20 degrees Celsius, and the water is having 10 moles. There will be a flow of heat from metal to water. The final temperature of the mixture was given as 26 degrees Celsius. What is the molar heat capacity of the metal? The molar heat capacity of the water was given as 75.4 joule per mole degrees Celsius. So here again, the heat which is lost by the metal will lose the heat, and that heat will be equal to the heat that is gained by the water at 20 degrees Celsius. That means that the number of mole of water times the molar heat capacity of the water times the change in temperature will be equal to the number of mole for the metal. Here we need to put minus sign to indicate that the metal will lose the heat. There will be a loss of heat from the metal. Then we have the N metal times the molar heat capacity for the metal times the change in temperature for the metal. Let's then put the values together. We have 10 moles for the water times 75.4, which is the molar heat capacity for the water, times the change in temperature for the water. The final temperature will be 26 degrees Celsius minus initial temperature, which is 20 degrees Celsius, which will be equal to minus 2 moles, the moles for the metal, times C metal, the molar heat capacity for the metal. So that is what we are asked to calculate. Then we need to calculate to multiply with the change in temperature, which will be equal to 26 degrees Celsius minus 150 degrees Celsius. The final temperature minus initial temperature. So we can do then the multiplication and the addition. Then we get the molar heat capacity of the metal, which is equal to 18.24 joule per mole degrees Celsius. We have here question 26. Question 26 is asking explain the terms endothermic reaction and exothermic reaction. That's it's number I. Number II is saying 2.6 gram of calcium chloride was dissolved in 260 gram of water in a coffee cup, a calorimeter, at combined initial temperature of 23 degrees Celsius. That means that the calcium chloride as a salt and the water they were having initial temperature of 23 degrees Celsius. The final temperature was 26.4 after mixing. We have the final temperature, which is 26.4 after mixing. That means after mixing, the temperature increased from 23 to 26.4. Calculate the heat of reaction. So that means the heat of reaction. Is the reaction exothermic or endothermic? So they're asking to use the specific heat capacity of water of 1.184 joule per gram degrees Celsius. Here, that means calcium chloride will lose the heat, and that heat is going to be gained by the water. So the same means that the calcium chloride, the heat which is produced by calcium chloride, or the heat of reaction, will be equal to a heat which is gained by the water to increase its temperature from 23 to 26.4 degrees Celsius. Let's start the answer on explaining the term endothermic reaction and the exothermic reaction. What is endothermic reaction? An endothermic reaction is a reaction that absorbs energy. The reaction which absorbs the energy, in that case, is called endothermic reaction. That means energy flows into the system via heat. So we are adding the heat to the system. So that means that the change in Q or the change in the heat of the system is positive, because the system is absorbing the energy. the energy of the system is increasing. If you have an endothermic reaction, delta Q will be positive. Exothermic reaction, contrary to endothermic reaction, exothermic reaction is a reaction that released energy. This reaction is exothermic when it is releasing the energy. Some of the energy stored in chemical bonds is being converted to heat. Then we are losing the heat in exothermic reaction. We are releasing energy as heat. The energy flows out of the system as heat. That means we are losing heat. Delta Q will be negative because we have exothermic reaction. So the reaction which liberates the energy, the reaction which releases the energy, in that case we are losing the energy, and delta Q will be negative because the system energy is decreasing. We are decreasing the system energy. Now let's go to II, where we have to calculate the heat. Now we see that the heat which is gained by the water will be equal to minus the heat of reaction, the heat which is lost by the salt. If you are dissolving the salt into the water and the temperature is increasing, that means that the heat which water has absorbed to increase its temperature is equal to the heat lost by the salt. The Q gained by the water, which is the heat gained by the water, will be equal to minus Q of reaction. That means that minus the mass of the salt times the specific heat capacity times the change in temperature. So here the Q gained by the water will be minus the Q, the heat of reaction. And if we are putting the Q gained by the water, it will be equal to the mass times the specific heat capacity times the change in temperature. Here we have the mass, which is 260 gram, times the specific heat capacity times the change in temperature. Then we see that the Q gained by the water will be equal to this value, which will be equal to minus 3060 198.7 joule. You can see that it is negative. And if it is negative, that means the reaction is exothermic. The delta Q is negative. In that case, we have the exothermic reaction. So let's move on to question 27. Question 27 is saying explain the terms thermal expansion and the coefficient of thermal expansion. The second sub-question of 27 is saying determine the length of the iron rod at 50 degrees Celsius if the initial length at 20 degrees Celsius was 300 meters. So we have the iron rod which initially was having 300 meters, and the temperature was increased to 50 degrees Celsius, and now they are asking what will be the length. The length after increasing the temperature. The coefficient of linear expansion of iron rod is 12 times 10 power negative 6 per degree Celsius. Let's start on the explaining the terms thermal expansion and the coefficient of thermal expansion. Thermal expansion, it is a tendency of matter to change. Matter change its shape, area, volume, and the density in response to change in temperature. If you are changing the shape, the length, the area, the volume, and the density in response to change in temperature, in that case, that's what you are referring as thermal expansion. Usually, not including phase transition. Here, the thermal expansion does not include the phase change. Thermal expansion is the tendency of matter to change its shape, area, volume, and density in response to change in temperature. Coefficient of thermal expansion is a coefficient which describes how the size of an object changes with a change in temperature. So this coefficient describes how an object changes its shape, how the object changes its length, its area, its volume as a function of the temperature. If you have a low coefficient, that means that we have a low change in size. Let's move to sub-question II. Coefficient of thermal expansion. So for the sub-question II, will use the coefficient of thermal expansion to calculate the final length. So here is equal to either 1 over the VO times the change in volume over the change in temperature. When you have the volume, when you have the area is equal to 1 over the area, initial area, times the change in area over dt. When you have the volume, this VO is initial volume. When you have the linear is equal to 1 over the initial length times delta L, the change in length dividing with the change in temperature. So this is the formula that we will use because we need to determine the final length after increasing in temperature. So this is alpha. If we are representing the coefficient of thermal expansion for linear as alpha, it will be equal to 1 over the initial length times the change in the length over dt. That means that the alpha times the initial length times dt will be equal to the change in air in the length. So the change in the air is equal to alpha times the initial length times the change in temperature. When we are dealing with the delta L, that means the final length minus the initial. So which will be equal to alpha times the initial times the change in temperature. So you can then put the values. So the LF we don't have. The initial one, we have the iron rod which has 300 meter as the initial length, is equal to alpha was given as 12 times 10 to the power negative 6 per degree Celsius times the initial length was given as 300 meter. The change in temperature, they are saying that when you change from 20 to 50, so that this means that you take the final temperature 50 minus initial temperature, which is 20. Then we need to determine the LF, which is the final length. Then we will get the final length, which is equal to 300.108 meter, an increase of 0.18 meter, corresponding to increase in 30 degrees Celsius. Let's move to question 28. Question 28 is saying a 50 milliliter sample of pure ethanol rests in 100 milliliter of container at 15 degrees Celsius. We have a 50 milliliter of pure ethanol, which is in 100 milliliter of container at 15 degrees Celsius. The coefficient of volume expansion of ethanol is this one. This is the coefficient of volume expansion. What will be the volume of ethanol in the container to be at 70 degrees Celsius? Here they are asking how the volume will increase if we change the temperature from 15 degrees Celsius to 70 degrees Celsius. So we are using the formula for coefficient of thermal expansion for volume, so which is equal to 1 over VO times dV over dt. Here also we need to use, if you are referring this coefficient of thermal expansion for volume as beta, that means that the change in volume will be equal to B times VO times dt. So that means this is beta. The change in volume then will be equal to beta times VO times dt. So the change in volume will be equal to the final volume minus initial volume, which will be equal to the coefficient of thermal expansion times initial volume times delta T. So we can then put the values. Putting the values, we have the VF, which we need to calculate, minus the initial volume is 50 milliliter, equal to beta. It was given as the coefficient of thermal expansion. Then times VO is the initial volume, which is 50 milliliter. Then times then the change in temperature, that means 70 minus 15 degrees Celsius. Then we get 55 degrees Celsius. In that case, we calculate VF and we see that the VF is equal to 53.025 milliliter, the final volume. So an increase of 3.025 milliliter to the initial volume. Thank you for this session. So next time we start on question 29. 29.